Dear students, let us start today's work uh, of understanding Lie derivative. So before going to the definition of Lie derivative, let us remember that the old coordinate and the new coordinate systems, the change in the old coordinates and new coordinate systems are related by this gamma uh, factor, where this gamma is gamma mu nu, or gamma is defined as the partial derivative of x dash mu by x beta, x dash alpha by x beta. And we also remember, we should remember that the scalar, how the scalar transforms from change in the coordinate system, the scalar more or less remains same. However, for tensors, this gamma mu nu comes, and this is the let us say that this is the old this is the new vector field, and that this is the old vector field at position x, and this is at position x prime, and how they are related, and they are related by this gamma factor, which is defined as that. So you can by this way you can define not only the 1 0 tensors but all tensors of different ranks. Okay, so once let us have this review this, let us now define uh, let us now consider an infinite small transformation, a very small transformation. How the transformation, just x mu goes to x mu dash, where there is a which is a old coordinate plus a very small with which is transformed to a new coordinate with a very small factor epsilon plus zeta mu. Zeta mu is the new uh, transformation in the coordinate, where zeta is a small parameter which is very small, less than 1. Therefore, it order of zeta square is considered to be 0. So we will neglect all the orders of zeta square which we get in from our next. Okay, so um, so how the definition of this gamma looks like. Uh, uh, so gamma is nothing but del by del x mu of x mu plus zeta plus epsilon zeta mu. Now this is, this is nothing but the delta function, and this is the ordinary the general definition of partial derivative. Okay, so now this gamma is defined in terms of the delta function and the partial derivative along with this small parameter epsilon. So proceeding similarly, you can always check that the inverse of this uh, the inverse of this transformation is given by this delta function minus of this partial derivative connected with epsilon. Okay, so these are the two relations which we will be frequently using, and let us keep this in mind. Now let us come to our original work of defining Lie derivative. So what is the Lie derivative? Let us first define it on a scalar, that is on a scalar field, and it is defined as, so let us say that L zeta is the coordinate by which, along which we are seeing the change of this scalar function phi. So it is defined as the limit epsilon goes to 0, phi at the new position, the old phi at the new position, and the new phi dash at the new position. Okay, so this is phi x dash minus phi dash of x dash by epsilon. And with how x dash is defined by x plus epsilon zeta mu. So we substitute it here. Next, we substitute it here in the, and we get this expression. Now let us expand this phi around x, and this is a general expansion, Taylor expansion. If I do this, and it will give this first as phi as a function of x, and then this is the partial derivative of phi with this factor, and all the higher orders of epsilon goes to 0 by our assumption and the choice of epsilon. So if I do this expansion, and then you see that this both this cancels, this is 0, so we get the definition of the Lie derivative phi along this coordinate zeta. So so it is defined as zeta mu del mu of phi. And if I want a covariant definition, it is zeta mu grad mu of phi. And because remember for scalar grad mu equal to del mu. So for scalar there is no change. You can always write you can write either del mu or grad mu, because for scalar this quantity remains the same. Now let us see how the Lie derivative is defined for a tensor field. So let us define L zeta of V mu. V mu is the tensor or the vector. Okay, this is the vector field, and this is defined as similarly as the scalar that we defined this vector at new position and the old vector at the new position. Okay, and again this is nothing but you can expand, you can write this is in terms of the gamma factor that we have just previously reviewed. Okay, so this becomes this in terms of the old vector, and this can be expanded in terms of around x. This x prime can be expanded in around x along this line. Now if I expand this, so this becomes the similar this becomes v mu x, this becomes epsilon zeta alpha del alpha v mu. Higher order terms are neglected, it is written as that. And however this is that first term is the delta function, and the second term is the epsilon del, the partial derivative. Okay, so now you check that these two terms will cancel each other. Okay, this already goes to 0, so we are left with two terms. And if I do this and if I make this change, so the Lie derivative of a vector is defined as epsilon zeta alpha grad alpha v mu minus del alpha zeta mu v alpha. Okay, so once this is done, so what we have is, so this is for a partial derivative, but from this for a general partial derivative. But from the theory of general covariance, what we know that this partial derivative can be written in terms of, always be write in terms of, in a special coordinate system we can always write in terms of the covariant derivative. So the covariant form of this Lie derivative of a vector v is defined like this. This is the covariant form, and this is the actual form which will be used in the curve space. Okay, this is the form of the Lie derivative of vector v. And once we know this, how the Lie derivative operates on a vector, we can generalize this for any rank tensor, higher rank tensor. Let us do this for a tensor of rank 0, 2. Okay, if I do that, so what we have, see, as this indices are on the lower indices, these are lower indices, so the upper indices have a negative sign, the lower indices should have positive sign. From our previous knowledge, you can also prove this explicitly, but no need. Okay, and for each indices there is one extra term. Along with this term, we will have two terms for which depends on the number or rank of the tensor. Okay, so you can now define, once we have defined the vectors, we can define 0, 2, 1, 1 mixed. If this is a mixed tensor, this will have been one would have been up with a positive sign, negative sign, and one with a positive sign. Okay, so these are how the Lie derivative for a scalar, vector, and a tensor fields are defined. Okay, now once we have defined the Lie derivative, let us have few conclusion from the above analysis. So one of the most important conclusion of the above analysis, you can see that the Lie derivative maps Mn tensor to an Mn tensor. Okay, it takes a tensor of rank Mn and takes it to a tensor of rank of the same rank. The rank doesn't change. Whereas for covariant derivative, it takes a Mn tensors. If I operate covariant derivative, it will make the final tensor a M of rank M and n plus 1. So this is the main difference between the Lie derivative and a covariant derivative, and it will be useful to us in many ways. Let us see. So why we are dealing with Lie derivatives? What is the option? Because we have partial derivative, we have covariant derivative. What is the need of Lie derivative? Lie derivative are very important when we consider symmetries of a metric. What do we mean symmetries? Symmetries means by if I change the metric in a certain way, if I change some coordinate of a metric in a certain way, the metric doesn't changes. So let us see this explicitly. Let us assume that let us make an infinitesimal coordinate transformation, say by zeta mu, and zeta mu is the symmetry of a metric, and zeta mu is the symmetry of a metric if the Lie derivative of g mu nu along this zeta is 0. What does this mean? This means that L zeta g mu nu, which is given by, because this is a rank of tensor of rank 0 2, we know how it transforms and how the Lie derivatives transform it, and we write this equation. However, we know that the covariant derivative of g is 0, so this is 0, and this merely transform this zeta alpha to zeta mu, and it is zeta alpha to zeta mu. So the Lie derivative of the definition of Lie derivative of g is nothing but grad mu zeta nu plus grad nu zeta mu equal to 0, and this should be 0 by if zeta is a symmetry, if zeta has some symmetry of the metric, represents some symmetry of the metric, then this should be equal to 0, and this equation is known as the Killing equation. Okay, so zeta mu is the symmetry of the metric only if it is 0, so this term should be equal to 0, and if this is 0, then this equation is known as Killing equation, and the solution vector zeta means all the zetas which does this, which gives the symmetry of a metric invariant, or which conserves the symmetry of a metric. This type of vectors are called Killing vectors. So if I move along the Killing vector, for over a metric, then we will not see any change in the metric. Okay, so Killing vectors are special vectors along which if I move, we will not find any change in the metric coordinates or metrics. Okay, let us see an example. Unless and until we do an example, we will not appreciate it. So let us find the Killing vector of a metric on a unit 2 sphere. What is the unit 2 sphere? Unit 2 sphere, it is a metric on a sphere of radius unity. So the line element is given by d theta square plus sine square d phi square. So once we have written this line element, you can find out the metric coefficient both for the lower indices and the upper indices. Okay, these are as they are diagonal matrix, only they are the components are inverse. Okay, and once we know this, we can calculate this Christopher symbols, and only these two terms survives: gamma theta phi phi, which is minus sine theta cos theta, and gamma phi theta phi, which is cos theta. So once we know, then let us have this Killing equation. We know that Killing equation is grad mu zeta mu plus grad nu zeta mu equal to 0. Here we have two coordinates, theta and phi. Okay, so let us first choose that both mu and nu are thetas. This you can always assume. And if I choose this, then what this gives us, this is only gives us one term because this is the same term repeating itself. So grad theta zeta theta equal to 0. If I write this in, if I expand this in terms of the partial derivative and the Christopher symbols, this is the equation which becomes, and we have this equation del theta zeta theta of the lower indices equal to 0. We can always make this lower indices go to the upper indices by multiplying with g theta theta, which we know from here is 1, and therefore del theta zeta theta equal to 0. So let us call this equation number 1. Now let us assume that mu equal to theta and mu equal to phi. Okay, so if I assume this, then the Killing equation is written in terms of this grad theta zeta phi plus grad phi zeta theta equal to 0. Now if I expand this in terms of the partial derivative and the Christopher symbols, and if I write explicitly the Christopher symbols, I will get this equation where lambda can be both theta and phi. And if I again expand this term, we will be having this equation where I have taken the lower indices to the upper indices with multiplying with g theta g phi phi. Okay, this I can always do. This I can also do this, and then this equation will reduce to a simple equation which is given by sin square theta del theta zeta phi plus del phi zeta theta equal to 0. Let us call this as the second killing equation, equation 2. And the third case is when we take mu equal to phi and nu equal to phi, both mu and nu are phi, then we have this equation grad phi zeta phi equal to 0. And then if I want to write it explicitly in terms of the partial derivative and the principal simple, I will get this equation. Again, I can take this lower indices to upper indices with these equations, and finally we have this equation del phi zeta phi plus cos theta zeta theta equal to 0, and let us call this equation 3. So any vector on this metric, on this surface or on this metric, which is given by this unit 2 sphere of unit radius, this if a vector has to be a Killing vector, they have to satisfy these three equations. Okay, and they can they can be a function of both in terms of coordinates. I can write zeta theta and zeta phi, and explicitly zeta theta can both be function of theta and phi. Zeta phi can also be a function of theta and phi, and there is no way of solving this, but however what we can do, we can guess some solutions and check whether these are killing vectors or not. If they satisfy, if we guess rightly, they will satisfy the three killing equation, and we then can conclude that these are the killing vectors. So the killing vector zeta can be written in terms of zeta theta del theta plus zeta phi del phi because of this form. This is a very general form. So let us first assume the first vector to be del phi. What if zeta of the first vector is del phi? That means this theta is 0, okay, and this is 1, okay. So if I assume this, then I find that the first vector which satisfies all the killing equation is del phi, and it is rightly, if you go back and substitute that in these three equations that we derive, you will find that this zeta 1, this killing vector zeta 1, which is equal to del phi, satisfy all the three equations. Okay, so similarly you can calculate the second vector, which is given by zeta 2, let us say, which is sin phi del theta plus cos theta cos phi del phi. Okay, this is, and you will, if you substitute this in all the three equations, you will again see that this vector satisfy all the killing equations, and so this is also a killing vector. And the third vector which satisfy the three equation is cos phi del theta minus cos theta of sin phi del phi. So these three vectors, these three linearly independent vectors satisfy all the three equations, and therefore for a metric on a two sphere, we have three killing vectors given by the three rotational symmetry of the metric. Okay, so you see that the killing vectors are related to the symmetries of the metric, and which can only be obtained by taking the Lie derivative. Okay, so this is the way of finding killing vectors, but let me tell you, killing vectors are very helpful in obtaining the symmetry of a metric, and they help us in reducing our problem, or to observe our problem and see what our problems actually are, and what is the symmetries of a metric we are looking for, how symmetric our metric is given by the killing vectors and the killing equations. But let me tell you that killing vectors and killing equations are not very easy to find. Although you can find a killing equation, but it is sometimes very difficult to find killing equation, and you can always try to find more and more killing vectors which satisfy the killing equation. Okay, so this is a comment that I should make, that although killing vectors are very important in finding the symmetries of the metric, they can be sometimes very hard to find. And as I've told you, we have already obtained the killing vectors when we were discussing about this Birkhoff theorem. You remember that I said that all spherically symmetric solution of Einstein equation, vacuum solution, have a time-like killing vectors. Okay, so remember that. So the del t there was the killing vector. So before we go if we end this discussion on Lie derivative and killing vectors, let us make some useful comment. Let us assume that if V and W are the killing vectors, that means that LV G mu nu equal to 0 and LW G mu nu equal to 0, then the operator, this is the uh, uh, this is the what this is called, this operator VW is also a killing vector. Okay, so that means that L VW is of G mu nu equal to 0. In general, if the metric is independent of a particular coordinate, say y, then del then we can always have del y G mu nu equal to 0, and then del y is the killing vector. That this is the form that I was talking about for this Birkhoff theorem when we are talking about Schwarzschild spherically symmetric solutions, right? We found that del t was the killing vector for that case, for the Schwarzschild solution. Okay, so killing vector also, this is another important thing that we have that you have to prove. A killing vector is a geodesic, so killing vector can also be a geodesic, but it can be a geodesic if and only if it is of constant length. Okay, you have to prove that. So this is a homework. Please take this and submit it to me. The another thing you have to prove, let us say that if k mu is a killing vector and x mu is a geodesic, then the quantity which is constructed by the killing vector and the derivative of the geodesic, let us say that it is qk, and this qk, you have to prove that this qk is constant along the geodesic. That means del by del tau of qa equal to 0. The fifth point that you should remember is, let us assume that this k mu is a killing vector and t mu nu is a conserved symmetric energy momentum tensor. This can be any tensor, only it has to be conserved and symmetric. Let us take this to be, let us say for our case which we know is the energy momentum tensor, and we construct a current like J mu k. K only defines that this is a this has this killing vector, and if I define it as T mu nu K mu, then this quantity J mu nu is covariantly conserved. You have to also prove this. And final proof that you have to give is, you have to prove that LV of G, this is the determinant of the metric, is nothing but twice G grad alpha V alpha, where V is the vector along which it remains invariant. Okay, let's stop here now and see what we have next. Dear students, welcome back. So next will be, this week we will be reading about Schwarzschild geodesics and the proof of Einstein equations. Okay, let us start from the equation for geodesic of R, and this is the equation that has already been derived when we are trying to derive the Schwarzschild equation. Okay, so this is given by d square r by d tau square equal to minus gm by r square plus l square by m square r to the power cube minus 3 gm l square by m square r to the power 4. This, purely Newtonian term. Okay, this is the important term. We know the solution of this equation. Okay, and knowing the solution of this equation, we will try to find out the solution of this whole equation and see how it changes our previous notion of Schwarzschild motion or Schwarzschild orbit. Okay, so we can always write this the left hand side d square r by d tau square in terms of the phi and tau. So we can write this as d phi by d tau into d by d tau of d phi by d tau dr by d tau. Once we do this, and let us assume mu equal to 1 by r, as we usually for classical mechanics we use this to find out the orbit equation. This helps us in many ways, and finally we invert or go back to 1 by r and then we check. So we do that here also. So if I do this, then I have my this definition of d mu by d phi, which is 1 minus 1 by r squared dr by d phi, and d phi by d tau is defined as L by mr square. So if I do this, then d square by d tau square can be written in terms of d mu by d phi square with a factor minus of L square m square r square coming in front. Now I substitute this in this equation. In this equation, substitute d square r by d tau square in terms of d square r by d phi square in this equation, and I get this equation to us. It gives this equation. So is minus L square by m square r cube r square by d square d mu square d phi square equal to minus gm by r square plus L square by m square r to the power cube plus this is the gravitational term. So I can solve this. I can again reduce this equation and write it in a compact form, which is given by d square mu by d phi square plus mu 1 by r integrated in terms of mu, which is nothing but gm by m square L square plus 3gm mu square. This is the old equation and this is the GR correction. Okay, so this makes things interesting. So let us, how to solve this? Let us first introduce a parameter epsilon, and so epsilon, and what we do this, we write this equation in this form: d square mu by d phi square equal to plus mu equal to mu 0. Mu 0 is nothing but this part, which is redefined as mu 0, which can also be gm m square by L square 1 by r 0 plus epsilon 3 gm by mu square. And you see that if I take epsilon to be 0, so we have this equation, which is nothing but our old Newtonian equation. So the case epsilon equal to 0 gives back the Newtonian equation, whereas epsilon equal to 1 gives back the GR correction term. Okay, so these are the two. Let us introduce this parameter and parameterize this equation in the first in terms of in Newtonian and then the Einstein or GR equation. Now we will look for a particular solution around the Newtonian solution epsilon equal to 0 of this form. Our total solution of the Einstein or the main Einstein equation, which is the full this equation, is, let us solve search the particular solution around it a Newtonian solution. Okay, first let us calculate the Newtonian solution, and then with this parameter epsilon and the solution mu e, we will find the general solution. But general solution is nothing but a solution around the Newtonian one. So let us first find the Newtonian solution. So what is the Newtonian solution? Newtonian solution is epsilon 0 of the order, this is of the order epsilon 0, that means which is nothing but epsilon equal to 0. So we have this equation. Yeah, remember we have this equation d square mu n especially makes that this is the Newtonian equation, and the solution is also of a Newtonian equation. So this is very easy to solve. This is a very known equation to us, which has a general solution of this form: mu n minus mu 0 equal to a cos phi minus phi 0. This can if I take the phi 0 initial phi to be equal to 0, okay, setting from some 0 of our coordinate system, the equation of the orbit becomes 1 by or mu equal to mu 0 1 plus e plus cos phi, or 1 by Rn equal to 1 by r0 1 plus e cos phi, where e equal to nothing but a r0. A is this constant. Okay, so we know that how this equation looks like and what are the orbits this equation gives. We know that e equal to 0 gives a circular orbit, and if the e lies between 0 and 1, this gives an elliptic orbit. It gives a parabola for e equal to 1 and hyperbola for e greater than 1. Okay, these are the known equations. Equations are known, orbits unknown to us. And for most astrophysical bodies, this E is between 0 and 1. That means the orbit of astrophysical bodies are always more or less elliptic. So if I now draw this ellipse, we have this, and for the ellipse, this is the phi and this is the r. So our motion of any heavenly body around some body which is sitting here is along this orbit, and this is called the perihelion of the orbit, and this is the aphelion of the orbit. And this is given by where r is minimum, that means mu equal to maximum, and d mu by d phi equal to 0, which has the solution sin phi equal to 0, and therefore phi n, we get that phi n equal to 2 pi n, and where n equal to 0 1 2. So all for 2 pi 4 pi we have this phi n goes to 0 and we have the solution. Okay, so this for Newtonian case, it always any heavenly body or any sun, moon, earth around any, say let us sun, and let us consider for earth moving around the sun, it always goes like this continuously. There is no change and this remains constant. This ellipse remains constant. However, let us see what happens if I take the GR correction into account. So if I take the GR correction into account, our equation now becomes d square u by d phi square plus u equal to u0. Now this is the extra term, where the terms come epsilon equal to 1, which will substitute later, but let us keep it here, epsilon plus 3gm u square. Okay, so so now we know that what is u. U is nothing but this Newtonian plus the Einstein solutions, as I assumed it to be. This is the solution which is around the Newtonian solution. So we can write the d square by d phi square un plus 3 un 0 plus u also un plus u0 equal to. Now let us expand u also again in terms of the Newtonian and the Einstein solution. Okay, if I do that and if I expand this, I will get this equation, whole equation, and say d square un by d phi square plus epsilon in terms of ue, un and epsilon ue plus u0 plus this whole term inside it. I can group this term. So d square un d phi square plus un minus u0, I can group this term. But why I have grouped this term? Because this is 0. This is the Newtonian equation and this is equal to 0, and this is the Einstein, this is of this order of epsilon, and all this are of the this is of epsilon and these are of the higher epsilon. The first term is 0, as I have told you, and taking only the order up to order of epsilon, because we are only considering epsilon equal to 1. Okay, and we are considering the GR correction is also of the order of epsilon equal to 1. If I group this terms which is of the order of epsilon, okay, then we have this equation from this equation. We have this 2 terms and this term, 3 terms. We have this 3 terms, and if I write this 3 term in terms of this, I can write un in terms of u0 plus our known solutions. Okay, so this will become d square u d phi square plus u equal to 3g u0 square 1 plus 2 epsilon cos theta. So, and therefore we have this, we write this term as u is 0, okay, and therefore we have this total equation. Now this is an inhomogeneous equation. An inhomogeneous equation has a homogeneous part and a particular solution. So homogeneous part is already known. Okay, we have already found that. Let us write this is as b cos phi, that be some other constant already used for the Newton calculations. And the particular solution, let us say that the particular solution is some b1, say use e0 plus b1 phi sin phi. This is a chosen one. For always, you remember that particular solution can always be chosen. It is very hard to derive. We can choose a function solution and then try putting it back on the equation and check. So if I put this back, if I put this back here, we will get b1 up dash equal to b1 sin phi. This I take the derivative of this one in terms of phi, and I have this double derivative, which becomes minus b1 phi sin phi. And if I put this back on the original differential equation which we have started to solve, that means this equation, then what we get is, we get this, which gives us b1 equal to eu0. Okay, so the Einstein equation becomes eu0, which is the constant term, plus this eu0 phi sin phi. So this is the total Einstein solution for the Einstein part, Einstein correction, or the GR correction. So GR, for if I write this u0 in terms of our known quantities 3gm by u0 square, I have this term, and this is the total solution for the GR correction. I can write this as and the total solution of the full equation, which has both the Newtonian and the GR part, can be written in terms of u phi equal to 1 by r phi, which is Newtonian plus the GR part and a higher order epsilon, but we are only considering epsilon equal to 1 and a higher order we are neglected. So our total solution becomes u0 1 plus 3 gm u0 plus e cos phi. This two are from the Newtonian part, and these are for the GR part. So, and we know that there is always a perihelion or a perihelion there, which for which du by d phi is 0. Let us say that, and this happens on phi n. Every phi n, if goes back for every 2 pi, there is a 0. And if I put this in this solutions, what we have in this, if I put the solution in this equation and solve, we will get that we have this solution, that equation minus sine phi n plus 3 gm u0 plus sine phi n plus phi n cos phi n equal to 0. And let us say that this phi n, now this is not a sine phi n. If for a equation sine phi n equal to 0, we have phi n equal to 2 pi n. However, this is not that. Let us say that due to all these corrections, we have an extra change in phi, which is given by delta phi n, which is the GR correction. And now if I put this in the original equation here, in this equation, and we solve this, this, what we get is, this will be sine 2 pi n is 0, but sine of 2 pi n is phi n, sine delta phi n, and delta phi will be small. What we get is this equation. Okay, we get this equation, and if I solve it for phi n, we have this is the total equation for the change in the phi n. Okay, it gives us the change in the phi as phi n goes from 0 to 2 pi. For change in the delta phi n, for every phi it moves, and for small limit, okay, this can be given in terms of 6 gm m square by L square, which is into n pi. This is the cumulative n pi. So this, what does this mean is, usually for the Newtonian case, what we have was, this was the elliptic solutions were always remaining same. The particle would have been gone and moved in the same ellipse. However, with these corrections, there is a shift in the perihelion, or the position of the perihelion. This is called the perihelion shifting. Okay, so it's our orbit starts from here, goes here, it remains same, but here, as there is a change in phi n, and it changes, the orbit changes, and it moves here, and then it goes here again, it comes back here, and it goes again here. So not only the perihelion is changing, the position of the perihelion is changing, and it goes like this. And this is also called the for Mercury, this is called the perihelion of the Mercury, and this is one of the tests for GR. One of the tests for GR, and for Mercury this was measured to be, delta phi was measured to be 43 seconds per every century. This was experimentally verified, and this was like, again, let us now see how the geodesic equation for photon or for light looks like, or what happens for lights, photons in GR. So this is the general geodesic equation which we have derived earlier. Okay, this is the Christopher symbol. Okay, let us try to solve this for photon. But we know for photon, we know that d tau equal to 0, so tau is not a good parameter. Tau is the proper time. For all massive particles, tau is a very good parameter, because it tells us how the velocity of the particle and the acceleration of the particle. But for photon, this is not a very good parameter, because we know that this goes to 0 for photon. So let us choose some other parameter, sigma, but this parameter has to be affine. Okay, but affine parameter is parameter which respects some property which we have discussed earlier. Okay, so now if I write the geodesic equation for photon in terms of this affine parameter sigma for a Schwarzschild geometry, what we have is, we have d square x mu by d tau sigma square plus gamma mu alpha beta dx alpha d sigma dx beta by d sigma equal to 0. Let us assume that we are in a plane, we are moving in a particular plane, so theta is fixed. Let us fix theta to be pi by 2. Let us say that in an equatorial plane around some in the geometry of Schwarzschild metric, which is a spherically symmetric one. So we are in a plane of that geometry. So now let us assume mu to be phi, and if I write the geodesic equation, we have this equation. But this is the old equation. Even this equation is even obtained from Newtonian case, which tells us that this phi dot is some constant L, and L is nothing but the angular momentum. And it also tells us in even in GR, this angular momentum is conserved. So this is an old equation. We just we just mentioned that this remains same as the Newtonian one. However, let us next choose mu to be R. What happens if mu to be R? This, if the geodesic equation of mu equal to R is already given to you, or you know this equation. This is a known equation which we have derived, which we have come upon when we are trying to write down the Schwarzschild metric or find out what are the coefficient of the Schwarzschild matrix are. Okay, Schwarzschild potentials. So this is the equation which you are familiar with. I have written this in terms of the Schwarzschild radius, RS. Okay, RS is the Schwarzschild radius, which is nothing but twice GM. Okay, so if I do this, we have this equation. This, let us say that this is equation 1, and remember, for photon ds is square equal to 0. That means d tau, which is equal to minus d tau square. If I write the ds square for photon, I again give back this equation for which connects dt d tau by dr d tau and d phi d tau, and let us call this equation 2. And if I substitute equation 2 in equation 1, this equation becomes very simple, which is given by d square r by d sigma square minus r by 3 by 2 is rs d phi by d tau d sigma whole square equal to 0. Okay, and however, we know what is d phi by d tau d sigma from our case mu equal to phi, and this is nothing but this L by r square. So if I put it back, we have this given equation d square r by d sigma square equal to L square by r cube minus 3L square gm by r to the power 4. I can write these two terms in terms of partial derivative del by delta del r of potential. Let us call this V GR effective. This is the effective potential of GR. You know the effective potential of Newtonian, which is also very well known to you. However, this is the effective potential of GR, and effective potential, this term is the Newtonian term. Remember, this is the special relativistic term. However, this is the GR term. This term is the new to us. So the effective potential of GR is the whole of this term. And if I now try to plot this, so let us first plot this VGR effective, SR is effective, only this term as a function of R. This coordinate is R, and we will get this type of curve. Okay, this is given by square. This curve is given by L square by 2 r square. However, if I plot the curve of this whole potential VGR effective, it gives curve of this type. Okay, so the potential of GR and potential of SR are very different, right? And one of the tasks is finding out what this potential means, okay, and what this potential tells us about the potential of GR, how a particle will move here and here. Okay, so this is a part you have to think about and discuss and come up with. So let us proceed now from here. Let us proceed, because we don't want not only want to have this potential, how the potential looks like, we want to we want to see how the photons behave in in case of a massive particle, in near a massive particle for GR case. So what now we will proceed as previously. Let us introduce a parameter zeta. Okay, parameter epsilon, where epsilon is a small parameter, and epsilon it goes to 0 for SR, and epsilon equal to 1. Sorry, this is 1. This is equal to 1 for GR. Uh, so therefore the equation can be written in terms of d square r by d sigma square plus h square by r cube minus epsilon 3 gm l square by r to the 4, and epsilon equal to 0 for SR case. This term is close to this, only this equation remains, and for GR this is 1, and whole equation is given by l square by r cube minus 3 gm l square by r to the 4. So proceeding similarly, d square r by d sigma square can be written in terms of phi and sigma and r, and if I do that, I know d phi by d sigma, and then d square r by d phi becomes this. So but d phi by d square becomes this, and this is the right hand part. And let us again use the similar formalism that we have used equal, write u equal to 1 by r. So what we have is, now if I do this, substitute this here, it becomes a very simple equation which is given by d square u by d phi square plus u equal to epsilon 3 gm u square, and epsilon, and for Newtonian case or SR case, this is the only equation, d square u by d phi square plus u equal to 0, whereas for GR we have this equation d square u by d phi square plus u equal to 3 gm u square. So for the order of epsilon 0, that means epsilon equal to 0, we have this equation, this, and let us call this special relativistic equation or special relativistic equation, and denoted by US. The solution is denoted by US, and which has a solution US equal to a cos phi by b sin phi, or 1 equal to AR cos phi plus BR sin phi. This can also be, this equation can, even in terms of a single parameter, instead of cos and phi, you can absorb it in sin phi. Okay, and this, if I do this equation, this is the equation of a straight line. If you don't believe it, just check yourself with substitution of the make appropriate substitution of r phi in Cartesian coordinate, and you will find that this becomes ax plus by equal to 1, which is the equation of a straight line. Okay, so the above equation, as I said, that the above equation can written in terms of phi, and this gives r sin phi equal to b, whereas b is the closest distance of approach. So what happens is that, so we can write the solution ur equal to sin phi by b. This is r sin phi by b. This r sin phi equal to b. So u are equal to b by r equal to sin phi by b. Therefore, u of r or u equal to sin phi by b. And let us find out what is the change in phi as particle moves from here to there. Okay, vary from r equal to plus infinity to r equal to minus infinity, or r equal to b. Let us say, let us say that particle is coming far from here when phi equal to 0. Okay, and it is coming here. This is the distance of the closest approach. So what is that change in phi? And if you do that, you will find that this is equal to pi. Okay, so this is the equation of a straight line. It is a straight line as phi goes to phi plus pi. So for special relativistic or Newtonian case, you see that if a photon in presence of near a very massive body or any body, it given the path of the photon is given by a straight line. Okay, so as phi changes from 0 to or phi 0 to pi, there is nothing happens on the path of the photon. It remains, it goes in a straight line. So this equation tells us that the light rays travel in straight line, which is a well-known Newtonian as a Newtonian solution, and which is proved by that. Now let us go to the general relativistic correction. What does general relativistic correction does? Let us again have this equation where we have put epsilon equal to 1, and we have this whole solution, and u square is nothing but sin square phi by b square. We have got back this written back this Newtonian term, and this can be written in terms of cos 2 phi. And if I see this equation, d square u by d phi square plus ug, let us say the solution is of this equation is ug, This is again a nonlinear solution which has a particular solution, and let the particular solution be of this form. Let us assume that particular solution of this form where C1 equal to Gm by 2s b square. So it is the whole of the particular solution is 3Gm by 2s square plus C1 plus 2 cos 2 phi 2 cos 2 phi. So the total solution up to the first order in GR is sin phi. This is for the Newtonian solution, and this is the GR solution. And for say, let us say that for n equal to 0, for phi at u equal to 0, when we put u equal to 0, we have the solution phi 0, and this is, let us say that u equal to 0. If I put this solution in this equation u equal to 0, we have we get back this equation sin phi 0 by b plus 3Gm by 2s b square 1 plus 2 cos 2 phi 0 equal to 0. And for small phi 0, what we get is phi 0 by b plus 3Gm by 2s b squared. This is the equation we get, and this can be expanded in terms of phi for small phi 0. And what we get is, for assuming phi 0 to be small, we have phi 0 equal to minus 2s Gm by b. What does this tell us? And working similarly for the previous case, we want to check what is the change in phi as r goes to from minus infinity to from plus infinity to minus infinity. We see that the total the delta phi, the change in phi is pi minus twice phi 0. Okay, and this twice phi 0 is nothing but, if I see that the photon is going from plus infinity to minus infinity, the change in the phi is twice phi 0. So the total deflection of light is alpha, which is given by 4Gm by b. B is the closest distance of approach. What happens? What this tells us that a photon or path of a light is gets bent when it passes near a massive object. Here is the phi and here is r, and this is the deflection. So if it was not if it was simply a Newtonian case, the photon will have been will pass like this, right? Asymptotic path, it will take the asymptotic path here. However, for GR, it doesn't. The GR on the mass affect the even the light path of the light, and it gets bent. The path of light gets bent, and then we have a deflection of light, and the total deflection of light from, if I check from plus infinity to minus infinity, is 4Gm by b. And this deflection was around Sun was experimentally verified by Eddington in 1990 during a solar eclipse, and for Sun he calculated this alpha to be 1.75 r/second. Okay, so this was the second solution of second verification of the Einstein equations. And so how GPS or GPS helps, or what is the help of GPS for Schwarzschild metric? So GPS is also a GR effect, which is not a Newtonian effect. So, and this effect can be understood even if I consider a Schwarzschild metric. Okay, so the as the vacuum or the space-time outside Earth can be approximated with a Schwarzschild metric. Okay, so this metric is given by, as you know, is d square equal to minus 1 minus 2 Gm by r dt square plus 1 minus 2 Gm by r to the power minus 1 dr square plus r square d1 square. Okay, so let us now consider an atomic clock at the surface of the Earth, which is given by, let us say the metric element or the elements are given by coordinates are given by dte for Earth, re at the radius re, it is at a radius re, and it has a particular angular coordinate theta 0 and phi 0. We also have, let us have some clock at the satellite which is moving around the Earth. The satellite is moving around the Earth, and it also has a clock, and that the coordinate of the clock is given by say dt GPS plus r orbit theta 0 and phi 0. It is at the same plane. The angular plane is same. However, these are at different radial distances, and the time is all changes. Okay. Let us say that time is given by dte, is symbolized by dte and dt GPS. So if I assume that the line element are same, or this is the line element should be same for both the cases. So what we have is as theta 0, phi 0 and r are constant, what we have is 1 minus 2 Gm by Re delta t e square is equal to 1 minus 2 gm by r, 2 gm by r orbit delta t square of GPS. Okay, so what is 2 gm? 2 gm is nothing but this Schwarzschild radius, and for Earth this is very small. It is 9 millimeter. You can check that. Let us assume that the radius of the Earth is 6400 kilometer, and the satellite is orbiting at a height of to 26,600 kilometers from the center of the Earth. Okay, which is usually the case for orbits. So now if I calculate this factor, this comes to be of the order of 1.4 into 10 to the minus 9, and this comes out to be 0.03 into the minus 9. Okay, now let us do is let the orbit clock is synchronized in such a way that delta t equal to 1, which is set at r equal to infinity. And if I said that delta t equal to 1, delta t GPS equal to 1, which is the clock at r equal to infinity, that means it has no effect of gr. So what we have is ds square of at r equal to plus 1. That means this quantity is plus 1. Okay, this r goes to, if r goes to infinity, this become 1, and this is already taken to be synchronized and clock, which is 1. So this term here in the right hand side becomes 1. Okay, if it becomes 1, so what we have is 1 minus 2 gm by re delta t square equal to 1, or the change in time in the Earth is 1 minus 2 gm by re to the power minus r, and which is, if we calculate, is 1.07 into the power minus 9 second. Okay, so this is very important. It looks very small. The change in time is very small, right? The difference in the change in time if I have a GR correction. However, this is not very small. This is of great importance because, let us say, if this delta t means if the change in time due to the GR effect, which is very small. If it looks like it's so small, in the change in due to GR effect is very small. Okay. However, if without the GR connection, what will we have? One will make an error per second in distance. How much distance in error if I make? So if I'm driving up my car and let us say that my GPS, my GPS is in the mobile showing the direction. Okay, and if the GR effect is not taken into account, what is the error which will be there? So the error will be, means this is the time, so the distance in error will be this into the speed of light, which is 3 to the power 8 meter. So the distance, so the error will be of per second. Error per second will be 0.46 meter. So in 1 second I will be having 0.46 meter. So means I will my mobile or the GPS in my mobile will show some other path. So within seconds I will lose direction, and I will take some other path, and I will be in a mess, complete mess. I cannot find my way to home if I don't know that. So GR effect are very important even for a daily practical use, and GPS uses that. Another way of looking into this is effect of GR is gravitational time dilation. Let us say that d square, the line elements are same for r going to infinity and for r equal to 0. All of the other coordinates does not vary. Let us say that only the change in we are only seeing the change in the time. It is the r and theta and phi are fixed. So what we have is, if I assume this where r0 tends to infinity, what we have is 1 minus 2 gm by r0 dt 0 square minus, and this is very near the earth, on the earth surface. So if I tend r0 to be infinity, what we'll have is, I will have delta t equal to delta t infinity, and means the actual time where there is no GR effect. This is the actual time, or the correct time, which should be there. This is the time which is affected by the gravitational effect, and this is given by, if I do the small approximation calculation, let us say that this is small. So what we have is 1 plus gm by re. So we see that the change in this is the actual time, and this is the time which we record in the earth. Okay, this is earth. Even earth is not a very big object, So this will be small, but if anything, if m is high, you can see that this will be a huge correction in there. So what we see is there is the clock runs slower closer to a mass. So this is the this is a clock which is close to mass. So it is twice, if it is, this factor is always positive, and this is say as the time for our clock records, which is near the surface of the earth or near any massive body, is much slower compared to a actual time. So this is known as gravitational time dilation. Next is, next us assume that uh, this is the initial part of, let us say that why a black hole is a black hole. We will be talking about black hole in much more detail later, but let us simple and small example. Consider a photon moving radially outwards. So what we have for photon, we know d square equal to 0. Okay, so it is moving in radially outwards, and phi are constant. So the line element is only have components of dt and dr. So it is the ds square equal to 1 minus 2 gm by r dt square plus 1 minus 2 gm to the power minus 1 dr square. And if it is 0, we can equate that, and we can find we can write dt in terms of dr 1 minus 2 gm by r. Let us write 2 gm by in terms of Schwarzschild coordinate rs. So it will be dt is equal to nothing but r dr by r minus rs. Okay, if, and this is the case for r greater than rs. However, we have taken check that we have taken the positive sign for, or for r greater than rs, and this will be negative for r less than rs. So for r less than rs, what we have is dt equal to nothing but r dr by rs minus r for r less than rs. So this is Schwarzschild radius, and this is the, say, some r. Okay, so what we say is that let us now find time taken to cover a distance from, let us say, r equal to r0 to r equal to rs. So from very inside of a star, inside of some inside of rs, which there a photon is starting its journey, it is coming radially outward, and it is crossing r equal to rs. So what is the time taken, the change in time? So this will be given by integration of dt, where it is and dt can be written in terms of this equation, where r goes from r0 to rs, and it is given by r dr by r minus rs. This can be written in terms of this. This is a trick we applied, r minus rs. Okay, so what it gives us, that it gives us a solution of r0 minus rs log of rs minus r, where r goes from r0 to infinity. And you can check that this tends to even infinity. This is very high. This tends to infinity. So what it tells us, that even light cannot escape the region r less than rs. So if a photon starts its journey from r0 to rs, even it cannot escape. It takes infinite amount of time to go there, to go out. So it cannot escape. So even no light comes out of this inside the rs. So this is, therefore, if as light doesn't come out, we get no information from inside what happening in rs, and this is known as black hole. So next day we will talk more about black holes, more interesting physics about black hole, but the initial